Howdy. All right. Didn't like today's lecture. Didn't like Teams. Didn't like the video. I don't even know if I hit record. It was disaster. So some of you missed it. So let's talk a little bit about what's going on here. We're ready for chapter 2. We've got our basic definitions here of an atom, smallest unit that retains the chemical properties of that element. Smallest unit of an element. But then the very next thing on this slide, tells me the parts of an atom. So they have to retain the chemical properties of that element. Now, we go into the book goes into a lot of detail on dates and they really let the facts get in the way, and the facts really kind of mess us up from knowing the overview of what's going on here. So it's 350 BCE. Democritus, he's a philosopher, all right, and so he's in ancient Greece. Really known for two things: philosophy and wine. Every philosopher I've ever met enjoyed their wine. Every person that I've ever hung out with and they drink way too much wine, they want to sit and tell you what they think of everything. So I don't drink wine with people anymore. I thought it was just because of lockdown. Oh well. So let's look a bit at Greece here. So, I stole this right off of Adobe. I did a Google search, man, whatever. So here's what I want you to know about Greece. Lots of hills, maybe a little path running through, see here, right? And then here's the beach down here. Now, what I imagine is these two guys, they're philosophers, but they're walking. There's two guys, and they said, "Let's go to the beach." And the stories always leaves out the little details, like I can imagine one of them carrying a half-empty jug of wine, and let's go to the beach. And while they're at the top of this hill, they can see the beach off in the distance, and it's just the beach. All right, and so you can see it. It's just the beach, and they get closer, and they can see different parts of the beach. They can see the parts that have rocks in them, and some that's wet sand, and some that's dry sand, some that has the grass growing up into it. And as they get closer, they start to see that it's made up of different areas. You've got some of the beach that has more shells in it, some that has more rocks, some that's just sand. But eventually, you get to the point where you can grab hold of the beach and you can scoop it up in your hand and you let it run through your fingers until you have one grain of sand. And that's when you have the smallest piece of the beach. And Democritus called that atomos, indivisible. Can't get any smaller than that and still be the beach. And we can divide all kinds of things up in our life that same way. And so his big leap in logic was to say, hey, what if everything was like that? What if a table, you got smaller and smaller and smaller in the components until you got to some tiny bit that if you went any smaller, it would no longer have the properties you associate with a table. So that's what we're doing here. We're looking at the smallest unit of an element that contains that. So we got a nucleus in the middle, protons, electrons. Man, this is, let's get an overall picture. We're going to look at one of the early basic pictures here, all right? And so this is probably one of the early pictures you're probably used to. We got the nucleus in the middle, and maybe around it somewhere, electrons. Man, you know what? Maybe you've seen, instead of this picture, maybe you've seen some kind of picture. And the electrons are going this way, and they're going that way, and maybe one's going that way. Oh, hey, that looks familiar. All right. So inside that nucleus, you've got your protons, P with a positive, your neutrons, N with a 0, and then outside it, you've got your electrons, E negative. So let's get our symbols again here. P, the positive, is a proton. E with a negative, an electron. That's your main one. That's the one that's going to save you a lot of writing when you take notes. N0 is your neutrons. All right. We'll learn about some other pieces in chapter 19. We'll learn about an alpha particle, a beta particle. All right. We'll learn about gamma radiation. Let there be more light. All right. And then we'll learn about a positron, which is an electron with a positive charge. All right. So we'll learn about those chapter 19. We'll worry about them then. But for now, we're going to focus on these protons, electrons, and neutrons. Now, while I've got this picture, I want to go ahead and introduce this word nucleon. We'll see that occasionally pop up in some of the reading. We'll see it pop up other places. Nucleon just means it resides in the nucleus. And so, for what we need to know, nucleons, protons, and neutrons, but not the electrons. The electrons are not contained inside the nucleus. All right. Let's summarize all these. So I'll work on erasing it while you guys look at this slide. All right. So we're summarizing. This eraser is terrible. Going back to paper towels. So an electron has a charge of -1. A proton has a +1 charge. No units. Oh, Dr. J, you're always insisting we have units. This is one of the cool things in the universe. I really, really like this. The electrons and the protons have exactly the same measurement, no matter what instrument we use. As long as we do it correctly, the electrons and the protons exactly the same charge, but opposite. And so by convention, we have called the proton the positive and the electron the negative. So that's why it's a -1 and +1 unitless, because that's by definition. All right, so neutron is 0. When we get to chapter 19, we'll sometimes think of a neutron as being a proton and electron stuck together. All right, and so that's why the charge balances out. Let's look at AMU. Now, AMU is atomic mass unit. Atomic mass unit. That's one of my favorite abbreviations. Please know it, okay? But it's already really small. It's like 10 to the -8 grams. Remember, grams a medium-sized paperclip. So 10 to the -8, that's already really, really small. But here I've got this 5.4 times 10 to the -4. So when I look at that, this in AMU, for an electron, 0.0054. Oh, I need another 0. 0.0054. All right. And then a proton has a mass of 1.00, and a neutron a mass of 1.00. Now, if I take these out far enough, if I go out far enough with these sig figs, the proton and the neutron are different. If I go far enough. But let's just round these to 2 decimal places. Then we see some really interesting stuff. So these are the same at 2 decimal places. And at 2 decimal places, the mass of my electron is 0. So the mass of our electron is 0. You can't say it has no mass. It has a mass. It just rounds to 0. We have a fancy word for that, insignificant. All right. One of the things that helps a lot in science is to learn prefixes and where they help. So we talked about significant digits, all right? But insignificant, in means not. All right? In means not. So insignificant, this mass is here. It just doesn't affect anything that we're looking at yet. All right? So it has a mass. It just rounds to 0. Okay. Insignificant, not. Be careful about that. Some of you will go into the medical field, and you need to be aware of this word. Inflammable. That means flammable. We have the French to thank for that. All right. So if you decide that you're gonna, some of you will work in hospitals, and it's real common for people in hospitals to decide that they're going to sneak out and go smoke. Maybe it's raining, or they got to hide because smoking's not allowed on campus like it is in Arkansas. It's not allowed. All right. So they're going to go hide and smoke. And here's this building out there. It's unfortunately usually unlocked. So don't go standing next to the inflammable canisters. All right. Go stand next to the non-flammable. Those are the ones that aren't going to catch on fire. Now, best advice, don't smoke. Don't smoke. All right. Once you start, it'll forever control you. Best case you could become is an ex-smoker. You'll never become a non-smoker again. It just, my father-in-law still gets cravings. All right. So here's we got some good advice there. We got our stats on this, easy stuff. So we're ready now for our discussion on these atomic symbols. Now in class, I went over a little bit on, the book does it too, so you can read a little bit on it. I'm big on alchemy. Matter of fact, when I was an undergraduate student, I wrote a thesis on it. All right. So alchemy, really pretty cool, really pretty interesting, but one of their main goals was to turn lead into gold. All right. And it had a lot bigger uses than just being rich. You could also use the same kind of process to purify your body, and then you would live forever. You could, if you were in the Christian view, you could purify your soul, and then you would be angelic. All right. So lots of, plus, you know, give yourself superpowers, invisibility, raining light feathers. All right. So we've got alchemy, but the key to alchemy was they had to hide their symbols. They didn't want anybody else interpreting them. Gold is useless if everybody's got it. All right. And so these guys wanted to hide their stuff. And so when we started getting into chemistry, one of the early differences in chemistry was the idea of sharing knowledge. And so chemistry, when we describe an atom, we tend to use these symbols. So I'm going to redraw this symbol over here. And hopefully we still can barely make it out. So C, a 12, a 6, and a 0 is what we have listed there. Now you'll notice there's nothing down here. Nothing down here. If I imagine a box around this is the bottom right corner. That's because if we write stuff like H2O, this on the bottom right is telling me I've got 2 of these atoms. All right. So easy enough. That's why we don't ever have anything in that bottom right corner. All right. The symbol C, it tells me this is carbon. Easy enough. All right. Then the number we see here is called the atomic number. And it is the number of protons. And that's how we determine which element it is. All right. So if I come over here to my periodic table and I come over here to C, here's my C, that 6 is actually above it. So that's where that 6 came from. Okay. So that's my atomic number. Number up here, it's called the mass number. And it's the protons plus the neutrons. Now, it does not include the electrons because the electrons have 0 mass. They do not contribute to the mass. All right. So protons plus the neutrons. And then over here, this is the charge. And it is equal to the protons minus the electrons, if you like to do this with algebra. Most students prefer to do this conceptually and not write out the algebra every time. And so here's where we get into our first kind of shortcut here. If that charge is 0, then the protons will be equal to the electrons. If that charge is a +1, we subtract 1 electron. Now you're not going to change the number of protons because that would change what the element is. All right. If it's a +2, you subtract 2. All right. If it is a -1, you add 1 electron. Okay. This seems a little backwards. At some point in chapter 2, it's going to hit you. This math seems backwards. Okay. And when that happens, I want you to remind yourself that electrons have a negative charge. And and that will guide you anytime the math seems backward. There will be several places that it seems a little bit, the math seems backwards. All right. So how do we work these kind of problems? What do we ask for? Well, typically what we'll be asking you for, we might have you identify the element based off of the atomic number. That's easy enough. We might have you, usually we figure out how many protons or how many electrons or how many neutrons. And where students get confused is not in doing the math. They get confused because they do the wrong math. So let's find the protons, the electrons, and the neutrons for this element. And for this particular atom, the protons, it has 6. And we got that from right here. So let's see if I can color code this. This is 6 because of that 6. All right. Now, the neutrons is usually the easiest one to do next. So remember, this is my protons plus neutrons, my mass number. And this is my protons. If I subtract those out, all that's left is my neutrons. So I'm going to come down here, and I did 12 minus 6, and that gave me my 6. All right. So neutrons, I got 6 from 12 minus 6. The electrons, we could do the math. Let's see if red's going to show up on this. Yeah, that will. All right, so 0 is equal to my protons. This is my charge of 0 minus my electrons. So here's my charge. All right. And then I can plug in my 6 for my protons minus electrons. Electrons equals 6. Easy enough. So that's where we get this 6. They all happen to be 6. This is carbon 12. It's kind of the basis. Matter of fact, it's our definition for AMU. It's 1/12 of one of these atoms. So try to say it's 1 proton or 1 neutron. They kind of vary a little bit, and so remember, if we take them out enough sig figs, they're different. If we do 1 hydrogen, 1 atom, it's a little bit confusing, especially hydrogen is lighter than air. It's hard to get the mass of. 1/12 of carbon 12. Oh, that's the name of this. All right, this is called carbon 12. So carbon dash 12. Oh, people that don't come to class, they always ask me, what do I do with that negative sign, Dr. J? I don't know. It's a dash. Carbon dash 12. All right. We don't actually usually give you all this information. Matter of fact, I don't have to give you the atomic number. Why? Well, all carbons have an atomic number of 6. Most of the time, the charge is 0. If it's 0, we don't put it. If it has a charge other than 0, I have to indicate it. But even there, we get a little bit lazy. Charge on this is 0. Charge on this one, plus 1. Right? So I just put a plus. What if I were to put a Cl with a minus? It's a minus 1. Or maybe I put an oxygen that's got a minus 2. I have to put the 2. All right. Maybe I want this sodium to be a plus 2. Got to put the plus 2. All right. But if there's no charge, we don't have to put it. So that means I could give you a word problem like this and say, find the protons and electrons, and let's pick oxygen. Let's do 16. Oxygen dash 16. All right. My advice when you're working these, work them the same every time. So if they ask for the protons and they ask for the electrons, go ahead and find the neutrons. That way these problems are always the same. There's no sense in stopping and trying to figure out which math you're trying to do. You do all the math, then you stop and say, hey, which one does he want? It really doesn't take that long because you can get into the habit of these. So oxygen. Now, that 16 they're giving me is my mass number. Okay. So I'm going to find the protons, the electrons, the neutrons. Well, we need some more numbers. So I'm going to come over to my periodic table. I'm going to find oxygen. It's over here. The number above it is an 8. And so I can come back and I can put that 8. That is my atomic number. Now, there was another number that was underneath that oxygen that was a 16. You might think it's this one. It's related. They're not the same. We'll talk about it in a little bit. This is the mass number. That one is the atomic mass. We'll deal with it in a minute. All right. Oxygen. What is the charge on this oxygen? Well, we don't see one. So if I don't see one, it's understood to be a 0. So go ahead and add those in if it helps you. Okay. They only had to give us one. Now, if this had a charge, they might say with a +1 charge, with a -2 charge. They tell us what the charge is. All right, so protons, I have 8. I'm going to go ahead and put that in blue so we know where we got it. We got that from there. The electron, I've got 0 charge. Now, we could work out the math and do all that, but what we're going to do is say, I have equal numbers of protons and electrons. In other words, I have 8 positive charges. I need enough negative charges to cancel out all of those. Well, 1 for each of these, that will take 8. So that's where I got that from this red up here. Okay? I'll throw off my color code. Hang on. There we go. 8. All right. So we did that conceptually. You could do it with algebra. It's the same process, same thought process, just different. Some people, I mean, that's what algebra is a nice way of summarizing this thought process. The numbers scare people. All right. Neutrons, 16 minus 8. That gave me 8. Nice and easy. Now, which one did they want? Well, here they're all 8, so okay, I'm going to pick that one. But it's very common for us to do these. And I asked about the protons and the electrons, and somebody will tell me the neutrons, because I guarantee you that's going to be an option when we do that. So do all of these the same. All right, so let's do a different one. Let's do, I don't know why I picked up blue, europium with a +3, and it is 63 down here. I'll go ahead and tell you that, save you from looking for it. And let's do 153. I like that one. Okay. So what if I wanted to find this and if I don't have this 63, I got to find EU. How you're supposed to do it? Well, you're supposed to go here and you start up here in the top left and you go through and you're looking for europium. Now, if it's actually written out, we have to figure out it's an E something, probably an EU, and we go through the periodic table I give you will have the names on it, so you don't got to memorize the names and symbols. So you can go through and make that whole list until you find it. Now, one thing that helps a lot, remember the masses that we see underneath these is the atomic mass. It's not the same as the mass number, but they're related, and you can get close by following the mass number. Now, these are no longer in order of the masses. The original periodic tables were, in fact, listed by the atomic masses. So when we get to like copper and zinc, you'll see a couple of places where they're out of order. But we're going to get close. So 153, I'm going to come over here. I'm going to go kind of down this row or down this column 1 and 6 and about 23 and 39, 132 and 222. All right. So I'm going to go this way. I get the lanthanum 140 roughly and about 180, somewhere in there. So I had to drop down here, and that's how I found my europium. So it can help guide you so you don't have to go through each of them. I never ended up looking over here. I just kind of eyeballed trying to find something close to 150. All right, so let's knock this one out. Protons, electrons, neutrons. How many protons? 63, right off the periodic table. How many neutrons? 153 minus 63. Oh, made that math too easy. 90. All right. Now, how many electrons does this one have? Well, okay, so it's got a +3 charge. What we need to do, what I would normally do is that, okay, I've got a +3. I'm going to subtract 3 electrons from my protons and get 60. All right, I subtracted 3. In other words, I have 63 positive charges. I need to cancel all of them out except 3 of those positive charges. So I need 3 less electrons than I have protons. Man, let's do the algebra. +3 would be my proton minus my electrons. So I'm going to have 63 minus my electrons. All right, so we're going to subtract here. I get -60 equals -E. Uh-oh. Not even showing all my work and all my setups. There's a reason I don't teach algebra. All right, we get 60. I'll let you figure out the algebra if you want to do that way. Me, I looked here. I said, I'm going to subtract 3. I can't change the protons. That would change my element, but I can change the electrons. Okay. So I subtracted 3. Remember, electrons have a negative charge. So I lost 3 negative charges. That's what gets me to my +3 charge. All right. So let's do a couple more here. Let's do H1, H2, H3. Protons, electrons, neutrons. Now, I want you to figure out this, and while you're thinking about these, I'll tell you a little bit about them. This is hydrogen 1. We usually just call it hydrogen 1. This is hydrogen 2, but it's so common we call it deuterium. It's responsible for a large part of our discovery and being able to use nuclear chemistry. Once we were able to make water, heavy water is what we call it, but water that's made with all deuterium, that was a big leap forward in being able to do a lot of our nuclear chemistry. Hydrogen 3, tritium. Oh, man, you hear about that in sci-fi movies and sci-fi books. They talk about that all the time. All right. Now, notice they're all H's, so they all have 1 proton. If they had 2, they'd be helium. All right. All of them have a charge of 0. That means they have 1 electron. Now, hydrogen 1 has 0 neutrons. Hydrogen 2 will have 1, and hydrogen 3 has 2. So when I look at these, remember I said I could make water, heavy water, at an H2? Well, it turns out they have almost exactly the same chemistry. They do everything hydrogen 1 will do, hydrogen 2 can do. So these have a very special relationship. They are called isotopes. Isotopes. Let's break that word down. Iso means same, but don't stop there. These are the same type. All right. In other words, what we have to have here is we want the same element or the same symbol. That's an even easier way to look at it, with a different mass number. If they had the same mass number, it would just be another atom exactly the same. All right. If it had a different symbol, it'd just be a different element, an atom of a different element. But here we have the same symbol, different numbers. Easy enough. Now, why are the masses different? That's the only real property of these that's different, is the masses. It's because of a different number of neutrons. Keep in mind the neutrons are buried deep inside the nucleus. The protons determine which element it is. The electrons we'll talk about on the outside. We spend most of our time worrying about the electrons and how they affect the chemistry. Neutrons just affecting the mass. They're just along for the ride. All right. So isotopes play an important role. Now, if I look at these 3 isotopes, they have different masses. We can find the average. So the average here would be 1 plus 2 plus 3, and I have 3 of these, and so I would divide it by 3. So I get 6 over 3, which is 2. All right, so the average should be 2 AMU. All right, so what I can do then is use this to get a rough idea of how many there really are. So here's my 1, here's my 3, here's nice and easy 2. If I had equal amounts of all 3 of them, 33%, equal amounts of all 3 of them, I would have this middle part would be where my average is. All right. Now the problem is, now we're doing hydrogen is lighter than air, but maybe you scoop down. If I get a handful of hydrogen atoms, they're not necessarily equally distributed. I'm not necessarily going to grab a handful of equal amounts of hydrogen 1 and hydrogen 2 and hydrogen 3. Matter of fact, when I do grab them, it's not going to be. I'll go ahead and tell you, it's not. And so what we have to do is to take into account how many hydrogen 1s and how many hydrogen 2s and how many hydrogen 3s we have. And that's called the atomic mass. It's a weighted average. You can think of it if I scoop up a handful of carbon atoms, if I get the total mass and then divide it by the number of atoms, I would get the average mass. Okay, and that's the atomic mass. And so we do a lot of fancy stuff with a mass spec, and it's a great way of getting a lot of information of the distribution of these isotopes. I'm not going to draw a picture and explain a mass spec to you. Mostly looks like a penis when you try to draw on a whiteboard. No fun. Really no fun in trying to draw in a class. All right, so let's think about what this atomic mass is doing. So we'll worry about the calculation here in a minute. If I had equal amounts of these, the atomic mass of hydrogen would be right at 2. If I had 50% of it hydrogen 1 and 50% of it hydrogen 3, it'd be right at 2. If I have more hydrogen 3 than these others, it'll be closer to 3. The closer to 3 I am, the bigger that difference is. If I have more hydrogen 1, it'd be closer to 1. So when I look on the periodic table, I'm going to come over here, I find hydrogen, and it says 1.008. Now, the ones we'll have in our book usually have more sig figs. This one has 4. It's nice and consistent. I got 1 million copies of this one. So we'll use that for now. If you need a good one, go to IUPAC. They'll give you a good free one. So I'll give you that link here. Oh, let's go here. Okay, so 1.008. In other words, this is like 99.97% hydrogen 1. I think it's like 0.29 for hydrogen 2, 0.01% for hydrogen 3. Really small amounts. Hydrogen 3 really doesn't contribute much. So when I grab hydrogen 1, it's almost all hydrogen 1. Okay. So that's my atomic mass. Let's figure out how we calculate this. So let's do, let's say we had, I got a nice example on here. Let's go ahead and do one here. All right. So this one, it says it's the sum of the abundance times the mass. Oops, sorry, can't say it. Sum of the abundance times the mass. Now the abundance, you're going to take a percent and you got to turn it into a fraction. So here they say it's 75%, 0.77% CL35 and 24. Now they usually don't give us CL35. They'll give us like 34.998, and they'll give us a whole bunch of sig figs. No, it doesn't affect the difficulty here. All right. So here you can see where it's done, but here's what we're doing with it. Let me flip this back over here. All right. So here's summarized out of that problem. Now I need to take these percents. You got to think about percents. We'll use those a lot. Let's say I get 8 out of 10 on my quiz, and I want to figure out the percents. Well, you take 8, this is what I made, divide it by what's possible, and then you do times 100. And so if it's a percent, it's got this part in it. So we need to get that out so we get rid of these percents. I needed a percent sign there. All right. So how do I do that? Instead of multiplying by 100, I'm going to divide by 100. So I'm going to take this 0.7577, multiply that by 35, and then I'm going to add that to 0. Let's put the 0 so you can see that they're decimals, not just where I didn't erase. 2423 times 37. And we'll add that up, and ooh, we'll get some magic number, and I'd have to figure out. Don't have the answer. Oh no. Wait a minute. 35.48 is what I got. Okay. So this is not hard. We give you these stuff. You just, the hardest part is remembering to divide by 100, multiply it by the mass. So if they give us a whole bunch more sig figs, use them. Not hard. All right. Now, what do we take home from this is more important to me. Those calculations, easy points. As long as you practice them, you've listened to this, you've read the book, you can do those calculations. Those aren't too bad. What if I see these? These are the two isotopes there. And the average there would be 80, right? And if I told you that it was 79.9, and we want to be able to figure out what kind of abundances are there. You can look these up in tables to get the natural abundances, but we should be able to get a rough idea if we knew that there were two isotopes, bromine 79 and bromine 81. So I have mostly 81, mostly 79, 50-50, a little bit more, a little bit less. Well, if it was exactly 80, I'd have 50-50. So it's just a little bit more bromine 79. It's like 51% to 49%. Easy enough, all right? These problems aren't too bad. Main thing I want you knowing is the difference between the atomic mass and the mass number. The mass number is for one atom. The atomic mass is the average of a collection of naturally occurring atoms. All right. All right. So let's jump over here. Let's see. I had mentioned that we would have to go and find some of these names when we're doing the protons and electrons and neutrons. Well, some of them have weird names. And so when you look for carbon, you expect it to be a C for carbon. Calcium can't be C because carbon already took it, so it's Ca. And well, these are some of the weird ones. Now, there's a bunch more. All right. So lead is from plumbum. That sounds like I got a flat butt, right? Okay. Natrium for sodium. That's what's in Na. So when you do sodium, you go looking around for an S and an SO and an SD. You're gonna get lost real fast. All right. So at Na, you don't have to memorize all of these right now. That's fine. You've got a periodic table. You're gonna have it over here. So when I say, "Hey, what is the element that has a symbol of W?" All right. And you're going to come through and get a multiple choice. And you'll have some things in there. If you kind of know, hey, that's one of the weird ones, then at least when you come over here and you look for it, you're going to come over and you're going to go through your list. How would I work this? I'm going to go through it until I find a W. All right. And so, oh, there's a W and it's tungsten. Okay. It's one of those weird ones. Now, when I'm doing these, if I give you the symbol and ask for the name, look it up. If you think you know that the Cl is for chlorine, double check it. Don't miss those points. And please don't. If I give you a periodic table, use it. All right. So, let's see, where are we going to go from there? We're ready for Dalton's atomic theory. Now, this is not the list that's in the book. The list in the book has 4 because they've combined some of these. Man. All right, so Dalton's atomic theory. He was a school teacher. He really kind of put the nail in to alchemy with this theory, and especially as we started kind of adopting it and using it. All right. This was kind of a nice way of saying any alchemist still out there trying to convince you they can turn lead into gold, don't give them any money. All right. Lots of kings lost their money. Man, it was. Whew. All right. So here's what he says: all matter consists of tiny particles. He called them atoms. Easy enough. He says an atom cannot be created, divided, destroyed, or converted into another type of atom. Well, that's the key. That no alchemy, no lead into gold. Okay. Number 3, he said atoms of a particular element have identical properties. Almost true. All right. So we'll come back and hit that one. Look at that one a little closer. Atoms of different elements have different properties. Okay. So, and then here's the key one: atoms of different elements combine in simple whole number ratios to produce compounds. All right. So eyeball what that's saying. What he's saying is when I have H2O for water, that it's never H2.5O. That I can have 2 to 1, but not 2.5 to 1. Simple whole number ratios. Never going to be 1.5 to 2 or something like that. Why? Because you cannot divide atoms. You can't have half of an atom. All right. So, number 6 says a chemical change involves joining, separating, or rearranging atoms. In other words, since you can't convert it from one form to another, if you want that atom, that element, at the end, you need to start with it. So, what's he talking about here? Well, we're just going to take the pieces. So, if I had this piece, it has 2 sets of these hydrogens connected together, and I got this piece. And if I do a reaction, all it is breaking apart these pieces and putting them together in different ways. Notice I still have 2 oxygens. I still have 4 hydrogen atoms. Now I've got a different compound. It's got different properties. These are all gases. And this is water. All right. And if we let it cool, it'll be to room temperature. It'll be a liquid. Easy enough. All right. Now, trying to think through these, what always helped me is to think of Legos. Think of Lego movie. All right. Replace any place you see the word atoms, replace it with Legos. Everything's made out of Legos. Legos can't be created, divided, destroyed, or converted. Well, that is true. That is the difference between quality Legos and the off brands. Quality Legos hurt. The off brands are dangerous because they do break when you step on them. All right. They break, you cut yourself. But the reason Legos hurt, they don't break. They don't give at all. All right. Now, can't convert into another type. So if I need this Lego that's got 3 pieces, I cannot take this piece and turn it into that piece. Just, it doesn't work. Doesn't work. All right. So when he says Legos of a particular element have identical properties. Now, what was the difference for Dalton? What when we were talking atoms? Isotopes. And what is the only difference they have? Well, they have differences in mass. Now, if we're talking Legos, what's the difference? Well, if I've got the 2x2 block and another 2x2 block, I can put them in the same place. Usually the only difference is color. All right, so the big difference there is color. All right, simple whole number ratios, and that's the key. If I give you Legos, you can't break them apart. Okay, and then this chemical change. So let's say I give you a pack of Legos, and I tell you to build a rocket ship, and you build it. And then I say, take those same Legos, you have to use all of them, and I'm not going to give you any more. Now make a pirate ship. You're going to probably have to do some rearranging to your rocket ship to make it into a pirate ship. All right. And so that's what's going on here. These are our rules until we get to nuclear chemistry. So when we're doing that chapter 19 or fundamental chemistry, when we're doing chapter 9, nuclear chemistry does not follow these rules. Matter of fact, that's exactly what nuclear chemistry is going to be doing. It's going to be creating, dividing, destroying, and converting. All right. So when I combine nuclei, I'll get fusion. When I divide a nucleus, I'll get fission. So Dalton's atomic theory, it works great until we get to nuclear chemistry. Okay. All right. So we're ready for Bohr's models coming up next. We'll deal with that on Thursday. And so we're in pretty good shape, but I want to show us some more about this periodic table. I want to kind of summarize the periodic table because we're going to be seeing it a lot. So here's let me see if I can get a better picture. If I go over here to my, looks like a little bit bigger picture. All right, so here's my periodic table. So this is a nice older periodic table. So it's got, I can tell, partly I can tell because it's not filled out all the way. Last year we added and named the official names for all these elements all the way across the bottom. All right. So sometimes you'll see placeholders. The last one. So if you see like 115 being UUQ, that's just a placeholder for Latin for 115. All right. So we've named them all. So that I can tell that this is an older periodic table because it doesn't have them all filled in yet. I can also tell by some of the numbering. So when I go left to right here, I've got a 1A, 2A, and those are Roman numerals. So let's review that real quick. So there's my 1 in Roman numerals, and this would be 2. What's that? Oh, it's 5, right? And this was 4. It's 7, right? Okay. 10. All right. Easy enough. Good. Good. So you remember your Roman numeral. So coming back to these, we've got Roman numerals with an A, and then over here I got A's, and then I've got B's in here. You know, we get some wackiness going on. Here's 1A, 2A. Over here is 3A, 4A through 8A. But here I got 3B, 4B, 5B, 6B, 7B. Some craziness going on with 8B. I don't know what's going on there. And then we got 1B and 2B. Okay. We'll worry about those in a little bit. And then over here, I've got these numbers 1 through 7. We see this word period. All right. So periodic table, what does that even mean? Periodic table means the repeating pattern. And the periods go left to right. So even though this is up and down, it's talking about things going left to right. So these are my rows that go across. Okay. And the chemistry changes gradually as I go from left to right. And it is repeating pattern. So I'm going to skip hydrogen and helium. And so if I take lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, if I put them in containers, I'd see the chemistry gradually changes. Shiny metals to powders to gases as we go. And then when I come back to sodium, it looks a lot like lithium. Magnesium, kind of like beryllium. Aluminum, not so much like boron. Silicon, a little bit like carbon. It's just kind of weird looking. All right. What's carbon look like? Pencil lead usually is a great way. Diamond is also carbon. All right. So phosphorus, sulfur, not quite like oxygen. Chlorine, argon, now they're gases. Then when I get to potassium, it looks a lot like sodium in its pure form. All right. And so it's a repeating pattern, kind of like notes in the music scale. All right. So periods go left and right. I can just say what period is bromine in. You'd find bromine. Here it is. What period is it in? It's in period 4. It's that simple. Okay. Now going up and down, a little bit tougher. We've got, those are called groups or families. Groups or families. All right. Now, a group or a family, I like the word family because they share similar traits, but a little bit gradual differences. All right. Now, these are going up and down. Now, they have, for the most part, a variety of names. Okay. So we're going to start with the first one here. This is going to be the parent of that family. So I could call this the hydrogen group or hydrogen family. It's also labeled 1A. So I call it 1A. It's also got a number 1 out here just underneath with no, it'll be in no Roman numerals, no A and no B. It's just group 1. So group, let's erase that. Try to erase it with my mouse. Group 1. All right. So it's 1A, group 1. Now, we will also learn it has a special name. So this set of names, these three kind of names, systems work for all of our groups. You can name them after the parent. You can name them with their A or their B numbering system. You can use the new system, which we'll talk about the difference between these two in just a second. But what I also want to focus on is we have to learn. So let me sketch my periodic table. All right. And we get this part down here. We have to learn the first two on the left, the last two on the right. So let's go ahead and get that list. All right. So group 1, and then we got group 2, group 17, and group 18 have special names that we need to know. All right, so group 1 is the alkali metals. Group 2 is the alkaline earth metal. If this is multiple choice, I got to keep those apart. How do I tell which one's which? Everybody always gets those confused. All right, I remember 2 is bigger than 1. All right. Ooh, that's a terrible. 2 is bigger than 1. All right. So if 2 is bigger than 1, then group 2 has a longer name. Works for me. Okay. Group 17, that's the last one over here, or next last one, sorry. That's the fluorine family, group 17. Those are called halogens. Halogens. Okay. Group 18 is called the noble gases. All right. You need to start with 17 and 18 when you're memorizing these. I'll almost always call the halogens. Group 18, we'll talk about the noble gases a whole lot this semester. Group 1 and group 2, sometimes, on the test, we'll call them alkaline metals and alkaline earth metals. A lot of times we just call them group 1 and group 2. All right. So you got to know these, memorize these 4 special names. But looking back at our periodic table then, so I've got group 1 and group 2. Now notice I said I've got this 1, 2. Let's talk about where these came from. So we also have 2 different types of elements here, and they've got them labeled up here: representative elements and transition elements. Now, representative elements, you'll also hear me refer to as main group elements. That's kind of the older name. It's a little offensive to people that study the transition elements because there's more of those. But why we call them representative elements is a lot of our rules that will start off then predicting the bonding work really well for these groups 1, 2, and 13 through 18. All right, so these have the A number, but the A numbering system only applies on the American periodic table. All right. And so 1A, 2A, 3A being over here. The Russian periodic table has 1A, 2A, 3A. So, and then 3B is over here. They use the A and the B for different things, and their argument is also then, hey, A comes before B, and they don't necessarily have all this craziness going on down here. And so you might say, well, I like the A's, makes it easy to tell. But great American style. We argue, and then when the Russians come back, hey, we invented the periodic table. So a new system, that's what we need. So we'll just number them 1 through 18. and it's actually much easier. And so we'll use this 1, 2, 3, and we just went 1 through 18 all the way across. Okay, so which ones then are representative? Representative. 1, 2, and 13 through 18. Alkali metals, alkaline earth metals. 17 is the halogens. 18 was my noble gases. You might even see those called inert gases in an old book. All right, inert means they do not react. If you label something in science says, hey, this never ever reacts, some smart ass makes it their life's work and they make them react. We've since made all of those react, but not under conditions we'll see in our labs. All right, so if you do a reaction with these noble gases, it's probably not going to be right. Okay, especially if you do it in lab. So 1, 2, 13 through 18. Easy enough. Transition elements down here. So if I take these words off, you should be able to still be able to identify them. Take these. I'll get rid of all this coloration. I mean, it's actually really easy. I just click on here. I go to format picture, and I don't know. I come over here somewhere. Picture details and correction and contrast. Crank that puppy. Oh no, the colors are gone. All right, so then we click undo so we can see it. All right, so really easy to do. We got plenty of these. All right, just download a new one, right? So don't rely on these colors. All right, I want you to know then. So here's sulfur. What family is it in? Well, sulfur is in 6A, 16, or the oxygen family. All right. What period is it in? Well, it's over here in period 3. Those are the kind of things I want you to know. I also want you to know sulfur is a representative element. Okay. And then I also want you being able to tell if things are going to be metals, non-metals, or semi-metals, or metalloids as our book calls it. And that is this line that comes down here. And this, drawing it on the wrong side. Okay, this line right here. This is our staircase. And that staircase, we're still debating right here. All right, so that staircase divides us up. So I'm going to sketch this out over here. Somewhere I bought a fancy new projector. I don't have access to it. So out in the RV. All right, so here I got 1 and 2. Here's my transition elements, inner transition elements. Here's my 13 through 18. Here's my staircase. Okay, so comes in here, comes in, comes in, comes in, comes in, and we're still not sure. All right. This way is my metals. Alkaline metals, alkaline earth metals. Dead giveaway. Iron, copper, things that we associate with being metals are over here. So what do we associate with metals? What are the properties of metals? Well, they're usually solid. All right. They conduct heat, electricity. They have luster, means they're shiny. All right. They are ductile, means you can make a wire out of them. They're malleable. Ooh, I don't want to try to spell that. Malleable. You hammer them into a sheet, so then you can fold them and do all kinds of construction with them. All right. Those are the properties we associate with metals. If I go this way from the staircase, they're non-metals. In other words, not these properties. Noble gases. They're not solids, right? Non-conductors then. The further that way, the more like a metal I get. The further away from my staircase, the less like a metal I get for these. Okay, so we might start with some solid and then work our way over to some gases. Now, touching the staircase. But when I say touching the staircase, corners don't count. It has to be top and bottom, or side to side. Top and bottom, side to side. If it's touching that, it's a metalloid. Oh, I hate that word. Metalloid. Ugh. It's not the metalloid industry. It's the semi-metal industry. All right, semi-metal. What's semi-metal? The sort of metal. They're sort of like metals. They have some of the properties of metals, but there's one exception. Aluminum is a metal. Aluminum is a metal. So when I look over here at my periodic table, aluminum is touching my staircase. It's the one exception. It is a metal, and it's a funky metal. It has a bunch of weird properties. Why? Well, let's see. Let's look at my overview. Oh man, I can't. I got all kinds of things that are aluminum here, but none of them I can show you. All right. But if I show you a piece of aluminum, you go, oh yeah, that's a piece of metal. We build stuff out of it, just like we build stuff out of metal. So aluminum's a metal. Otherwise, boron, silicon, germanium, arsenic, what do we got? Antimony, telomonium, polonium, actinide. Just running right down this, if it's touching that staircase. So you kind of want to know where that staircase is, because not every periodic table has it where you can see that easily. All right, so kind of learn to see where the staircase is. Metals over here, non-metals over there. If I asked about sulfur, I want you knowing. You can bet we're going to ask about aluminum. You can bet we want you to know that's a metal. So that's your basic rundown of the periodic table. We'll use it a lot. So remember, the numbers on the top are our atomic numbers. Numbers below that are atomic masses, which are the averages, the weighted average. They're weighting by their natural abundance and their mass numbers. Okay, so all kinds of stuff going on. We'll use this periodic table a lot. So that's long enough. Whew. So we'll go ahead and stop there. I'll get this uploaded for you. And so we'll see you on Thursday. Have a good one.